Okay, so for example, we may define some event A to be equal to mean a coin lands on heads. And we would then say the probability of A is equal to 0.5. So this indicates how likely event A is to happen. Is this? I felt like I was too loud. Can you guys still hear me now? It's good. Okay, so this indicates how likely event A is to happen, and so the probability of any event, okay, is written this way. We write P and then parentheses, or PR and parentheses. Okay, so probability. This is. Can also be written with just a single P without the R. Is always between 0 and 1. So if probability of B equals 1, then that means event B always happens, okay, or is certain to happen. And then over here we can say if probability of event C is equal to 0, then event C never happens. So whatever the events are, you put that in the probability thing and you assign a number to it, or you calculate a number for it. You do not write or say B equals 1 or C equals 0, okay? Because the event is not equal to 1, it's the probability of the event, okay? The event itself is not a number. Okay, we are talking about the probability of the event. Okay, so we might say there, you know, in depending on the forecast, we might say there is a 40% chance of rain, or a 80% chance of rain, but we don't say 80% is rain. We're talking about the chance of rain. You guys are all craning your necks around each other's heads, so let me just see if I can zoom out here. I don't know how to do that. Okay, so I'll let you guys finish copying that down, and we'll talk more about probability rules here. So far, so good? No. Okay. How about no? Okay. So we have, so let's continue on and say A is the coin lands heads. Okay. we have something called a complement. This is the complement of event A. And this means this is basically the event that A does not happen. Okay, so a complement can also be written as not A, or it can also be written as A, and we call this prime. We put a little tick mark, and we call that A prime. And so if A is the coin lands heads, what is a complement? It would be the coin does not land heads. Okay, so if A is the event that the coin lands heads, the complement of A is the coin does not land heads. Now we can simplify the world and say if the coin does not land heads, then that means the coin lands tails, but technically there are other things that could happen. I don't know, the coin could land on its side, the coin could get eaten by a eagle midair. You know, anything could happen. We could simplify the world and then say, you know, say in a simplified world, this means the coin lands tails. We could say that. But it is, if we're talking about a complement directly, it just means not A or not the coin lands heads. Is the distinction there clear? Okay. And so if probability of A is equal to 0.5, then the probability of not A is equal to 1 minus the probability of A. And in our case, it would be 1 minus 0.5, which is equal to 0.5. Oops. So just to check your understanding, let's say we have some kind of bag here, and inside the bag we have different balls, and we'll say the probability of selecting something white, we'll say is 0.2, okay? So then what would the probability of selecting something that is not white? 0.8, right? We do 1 minus 0.2 and we get 0.8. Okay with everybody? Yes? All right. Here, I'll color these in. Okay. Now, we have to make a distinction here. We've got something called empirical probability and theoretic probability. Okay, so what does the word empirical mean? This is your SAT vocabulary word. Empirical means nobody, everybody fails. based on evidence. Okay? All right, well, that's what it means. So in our case, we're talking about probabilities based on evidence. So empirical probability is a probability calculated from actual observations. So let's say you had never seen a coin before. Okay? So you've never seen a coin. So here's our example. Okay, you've never seen a coin before, but you want to know how likely is this coin going to land on heads. Okay, so in other countries with coins, do they still call, what do they call the two sides of the coin? Is it heads and tails, or do they have a front and, is there a name? Huh? I mean, I know it's like obverse and reverse is like the technical name, but I know we have international students, and I know you have coins in your countries. I'm just curious, what do they call the two sides of the coin? What does that translate into? Crown in the back. and do you say called crown or the other side when you flip coins, obviously?
Krona or flower.
Okay.
Flower is like a flower.
Okay, so you say crown or flower, and all the coins have crown or flower? There's only. Okay. All right. I don't know. Because in American coins, all the coins have a head or a face on one side, and the other side has just a different design. But all the coins have crowns and flowers? No.
No, it's our king on the crown side.
So king.
Yeah.
Okay, king, and something else. Okay. Yeah, no. I was just curious. I don't know why we call it tails on the other side. Well, I mean, it's not like we see someone's tail on the back. We just call that side tail. Okay, anyway, well, thank you for answering that for Sweden, right? Okay. You know, last time I had Swedish students, international students, they promised that they would bring Swedish fish to class because I was talking about Swedish fish, and they said the Swedish fish you have here in America is not real Swedish fish, and I said, well, I like my fake American red candies. All right. Anyway, okay. So let's say we've never seen a coin. Let's say we've never seen a coin. Okay. We have never seen a coin, and we don't understand. We don't know that it has an equal chance of landing heads or tails. Okay. So one way to kind of investigate this probability is just to carry out a bunch of experiments, in that we flip a coin and we record whether it has landed heads or tails, and we do this many times, and we keep track of how many times it landed heads, how many times it landed tails, and that gives you an idea of the probability that it lands heads or tails. Okay? So we can, get an idea of the probability by flipping a coin many times. Okay, we keep track. How often the coin lands heads and how often it lands tails. Okay, and then we then divide what do we divide? We divide number of heads by number of flips, and this gives us our empirical probability of landing heads. Okay, so maybe, so after 1,000 flips, maybe it landed heads 508 heads divided by 1,000 flips. My probability would then be 0.508, and this is the probability of getting heads based on our evidence. I just want to make sure conceptually that this concept is okay. Right? And so we see empirical probability show up for a lot of situations where they would be rather difficult to calculate actual math. Okay, so the rest of today's class will focus on theoretic probabilities, which we calculate using mathematical rules. Okay. I'll let you guys finish before I continue talking here. So we see empirical probabilities show up a lot of times in sports. Okay, they don't call them empirical probabilities, but for example, we've got the MLB postseason for baseball, and a lot of times you'll show a batter will come up and they'll put up the batting average, okay? And this is basically how many times the batter achieves a hit divided by the number of times the batter had an at-bat, okay? Which is almost the same as a plate appearance, but the formulas are a little bit different. But basically, you know, how often did the batter hit the ball and make it to first base, okay? Divided by how many times has the batter, you know, stood at bat, okay? And we do that, and we get a number, maybe 0.295, okay? And so this essentially gives, you know, a viewer watching TV, we can say, oh, this batter has approximately a 0.295 chance, assuming everything else equal, has approximately a 0.295 chance of getting a hit, okay? You know, and you know, if you follow baseball, you know, they've refined a lot of these statistics and things like that. But these serve as kind of a sense of, you know, a prediction of how well the baseball player will do based on his past performance, okay? And so, you know, maybe a pitcher will come up to bat and it will have like a batting average of, you know, 0.092 or something like that. And that means the pitcher has, you know, less than 10% chance, you know, based on the past performance, okay? So these they don't call them probabilities. We call these statistics when it comes to baseball, but essentially that's what they are, okay? We're looking at how often a batter successfully reached first base on a hit or whatever base, divided by the total number of observations, okay? And this gives us a sense of the batter's performance, okay? Theoretic probabilities, on the other hand, okay, are calculated or are found using mathematical rules. Okay, so, you know, if you've never seen a coin before, you could flip the coin 1,000 times and say it landed heads 508 times, therefore my empirical probability is 0.508. You know, you can imagine I don't know, this would be a very terrible TV show, but somebody could flip coins and they could have the running, quote, batting average, but it would be the landing on heads average. And, you know, well, you can make anything exciting with proper editing and commentary. And, you know, it lands landed heads 0.508, okay? Now, according to the mathematical rules of probability, we say something like, there are two sides to the coin. You know, each side has equal probability. Therefore, the probability of heads is 1 out of 2, or 0.5. So this is the theoretic probability. According to our understanding of physics, coins, and math, we say the theoretic probability that a coin lands heads is 0.5. And there's a whole bunch more rules that really the rest of today is going to focus on. We reconcile the two, the empirical and the theoretic probabilities, with what we call the law of large numbers. And what the law of large numbers states is that in the long run, as we perform more and more trials, of a random experiment. This is just a fancy way of saying as you flip the coin more often, or as you repeat whatever it is that you're doing more often, the empirical probability we observe will get closer and closer, or will get closer to the theoretic probability. Okay, and so this is what happens in the law of large numbers. It's in the long run. So of course, in any short-term thing, you might see a streak of a bunch of heads or a streak of a bunch of tails, and that might, quote, throw things off a tiny bit. But in the long run, you know, after millions and millions of coin flips, you're going to see something very close. Your empirical probability will be very close to the theoretic probability. Okay? But a lot of times, you know, maybe the math is too complicated, or we don't know the formulas to figure out the theoretic probabilities in all cases. So we have to use empirical probabilities. And, you know, with baseball, is there a math formula that we can say, you know, look at a baseball player, you know, measure how long his arms are and measure how much he can lift, how much he weighs, how fast he runs, and then put this all in a formula and say, boom, he's going to have this batting average? No, we don't have anything like that, right? So we just have to look at their past performance, say this player did very well in high school and in college and in the minor leagues, and therefore we're ready to make him a professional big league player, and we hope that he does well, or something like that. We base the value of the players based on their performance, their past performance, because in effect this gives us an idea of what their future performance is. We don't have formulas for people, at least for baseball. Other things we do. So that's what we have. Okay, and so the rest of our class is all going to be about learning these mathematical rules for calculating theoretic probabilities. Okay, and so these rules are easy when we talk about things like flipping a coin, rolling a die, or picking a random person, okay, or picking a random object. we can talk about theoretic probabilities. And so the rest of today is going to focus on that. Are there any questions so far?
About counting cards.
Counting cards? What do you mean by?
I learned something in class that would pertain to counting cards. Not that I would use it now.
Yeah, okay. Well, so in this class, like today's lecture is not going to give you any tools in counting cards, but the rules of probability definitely go into why people count cards. When you count cards, you're basically keeping track of the probability of what's going to happen in the deck, right? When you first start off with a deck, you know 50% of the cards are red, 50% of the cards are black. Or, you count cards for blackjack, so you know 16 of the cards have 10-point values, 4 of the cards are aces, and the rest are point cards. So you know 20 of the cards are basically favorable for getting blackjack, and 32 are not. And when you're counting cards, you're keeping track of those cards, so you have an idea of the probability that exists in the deck. That's all that's doing, okay? And it's an application of the rules of probability. But ideally, well, if you count cards successfully and don't get kicked out of the casino, you could make a profit in Las Vegas. But generally they discourage that, and they might ask you to stop playing. And it takes the fun out of the game. It does so. But anyway, let's talk about some basic rules. What's that?
They haven't got me yet.
Okay. Basic rules of probability. Okay, so we have what we call simple outcomes, and this would apply to situations where the different outcomes have the same probability. Okay, so examples are things like rolling a die. Each face has the same probability. Picking a card at random from a deck. Or, picking a person at random from a group. So you'd have, we're assuming that each person, each card, or each face of the die has an equal chance of being selected. Each person, each card, or each face of die has an equal probability. So those are simple outcomes. And then so if we have some event A, which is made up of a combination of these outcomes, we say the probability of A is equal to the number of events or outcomes in A divided by the total number of outcomes, I should say. So for example, let's say we want to know what is the probability of picking a face card from a standard 52 card deck. Okay, so the face cards would be Jack, Queen, and King in each suit. Ace is not a face card. There's no face on an ace. High value card. You need it in poker, but it's not a face card. Okay, so what is the probability of selecting a face card from a standard deck? Out of? 12 out of 52. Okay? So 12 divided by 52. Is that okay? Jack, Queen, King in each suit. There's 4 suits total. So we have 12 cards that are face cards, 52 cards total. So this simplifies to 3 out of 13, or 12 out of 52, 0.2308. Is this okay? All right. Hold on, go back. Go back. Okay, hang on a second. I just did 12 divided by 52. I have no idea. I try not to look at my phone while I'm teaching a class. All right, do we all have this down now? Okay. Oops, actually, no, shoot. Where are we? XL10, here we are, okay. All right, so let's talk about, maybe we have a table of people. Okay. Okay, so let's say we have men and women, and let's say we ask people, are you liberal or conservative? Or we'll say moderate, okay? So we'll say liberal, moderate, or conservative, okay? And this is just, we just ask you, if you had to pick one of these 3 to identify yourself, which do you pick? So we're not going to ask you, how did you vote, or how do you feel about this situation, this topic or whatever. We just say, please self-identify, right? So people might have different definitions, but if someone says, I think I'm a liberal, then we say you're a liberal. And if they say, I think I'm moderate, we say, okay, you're moderate. And if they say I'm conservative, we say, okay, sounds good. All right, and so let's say we asked, we have a room of 100 people, okay? So we have a total of 100 people in this room, and I don't know, okay. Let's say 46 are men, 54 are women, and I have no idea what numbers to put in this thing, but let's say 25 women say they are liberal, 20 say they are moderate, so what does that leave me? 9 who say they are conservative. Okay, I don't know where I'm asking these people. So, and then let's say we go with the men, and we'll say 20 and 21 and 5. Okay, just making up numbers. Okay, so these numbers are all made up. So, okay, so just in case it's not clear, the numbers in the table are made up. Well, sometimes people ask, where did you get that number 5? And I'm like, oh, I just made it up. Okay, so the numbers in the table are made up. Okay, but we can use this to answer questions about probability. So how many liberal people do we have? 46. We have 25 people who are moderate and 29 people who identify as conservative. And let me just make sure this adds up correctly. Okay, good. That adds up to 100. Okay, and so I could then ask a question like this. Okay, so we're going to pick someone at random. We will pick one person at random. Okay, so that means all 100 people in this table have an equal chance of being selected, right? 100 persons have an equal chance of being selected. Okay, so I could say, what is the probability that a randomly selected person dot 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 dot, and we're going to say is a woman. Okay, what is our answer? Yeah, 0.54, right? I say we do this by 54 out of the 100 people is 0.54. So don't say the probability is 54. It's 0.54, okay? Because the probabilities always have to be between 0 and 1, right? We covered that on the very first page. So the probabilities always have to be between 0 and 1. So if ever you get a probability that's bigger than 1, you have made a mistake. Okay, so that's a big clue. If you ever pick a probability that's bigger than 1, you have made a mistake. If you see that on a multiple choice test, you know those answers you can eliminate immediately, even before you read the rest of the question. Okay. All right. We could ask, what is the probability that a randomly selected person is conservative? Okay, and your answer there would be 0.29, right? So we 29 divided by 100. Okay. We could also ask, a randomly selected person is a conservative woman. .09, right? So 9 people in this room of 100, or in this table of 100, 9 of them are conservative women. So our answer is 9 out of 100, or 0.09. Okay, and this is very important that we write 0.09 and not 0.9. Okay, because 0.9 is 90%. That's a very different story. Okay, that might be applied to, I don't know, if we went to Utah, then no, nothing wrong about Utah. Just demographically, it's very different than Los Angeles. Yes. So that's a different, we have, these are different questions, what you're asking, okay? All right, so this is a probability that a randomly selected person, what's implicit here is that the randomly selected person is, we're selecting from the group of 100, okay? Now, I could, I'm going to go copy this table onto the next slide, okay? Can I go on? Next slide? Okay. So I'm going to move this over to the next slide, and I'm going to say I pick a person, okay? I have randomly selected a person. Okay. And then now I'm going to give you a key piece of information. I'm going to say this person is a woman. Okay, so the person I randomly selected is a woman. Okay, now I'm going to ask, what is the probability she is conservative? Okay, so what is our fraction that we would do here? We do 9 divided by 54, right? Because now that you know that the person is a woman, you know that it has to be one of these 54 people. So we do 9 divided by 54, and indeed we get 0.1667. Okay, if we round off to the 4th decimal place. Okay, so this. Let me flip back a slide here. Okay. Okay. So these answers I'm going to write in symbolic form. Okay. So these answers can also be written. So go a little bit higher in your notes. This is going to be probability of selecting a woman is 0.54. And I would write probability that somebody is conservative is 0.29, and this is going to be probability that someone is conservative and woman. Okay. So notice what I've written here. I wrote probability, conservative, and woman. So this is the probability that someone we randomly select from the entire table is conservative and a woman, or is a conservative woman. Did we get the symbolic or equation form down? Over here, we know that the person we've selected is a woman, and we want to know what's the probability she is conservative, okay? So in statistics, we write this as what is the probability of woman, and we use this term given. I'm sorry, I have this wrong. What is the probability of conservative given, meaning we know that this person is a woman. Okay, what is the probability of conservative given? Okay, so symbolically we write probability that someone is conservative. Okay, and then this is very important, I write a vertical bar woman. Okay, so this means we know the person we selected is a woman, so we know we're down to these group of 54. What is the probability she's conservative? And this is going to be 9 out of 54, or 0.1667. Does that make sense? Okay, so then I'm going to put an equation up here, and you tell me, don't shout out your answer, okay, but I want you to think of 2 things. I want you to think, what does this thing ask, and what is the answer to this thing, okay? So I'm going to write probability of okay, so write down on your paper what you think this means, and write down the number that you think this thing is equal to. Okay, what do we have?
0.10.
Okay, so our answer is going to be 5 divided by 46, so we have 0.1087. Yeah, how dare you tell me 0.1086. So we have 0.1087 if we round to 4 decimal places, and this is what is the probability of moderate given male. Okay, so we select someone, we know this person is male. What is the probability that this person is then moderate? Okay, now distinguish this from, I'm going to write this, probability so what's the difference here? So this is going to be 5 over 25, which is 0.2. Okay, so over here, so this means, you know, so imagine this. I'm going to write, I have randomly selected a person. I have selected a person. What do we know about this person? This person is moderate. Okay, and then the next question is, what is the probability this person is male? Okay, that's what this is saying. We know this person is moderate. What is the probability this person is male? Let me actually, I guess I'll write the parallel story up here. Okay, and so up top over here, we've got, I've selected a person. This person is male. What is the probability he is moderate? Okay, so please look at these two situations and make sure you understand the difference between this one and this one. Is this clear with everybody? The difference between moderate given male and male given moderate. Are we okay there? Okay, so then just to practice here, I'm going to flip to the next slide. Can I do that? Yes? No? No. Okay. So I'll let you copy. Well, it looks like the Dodgers have forced to Game 5.
Nice.
So And the Cubs, yeah. Cubs move on. What a day to be alive. Okay, I'm gonna go on now. Is that cool? All right, so let's take a look at this. Make sure we got all of these differences here. Okay, so quick quiz based on this. I'm gonna just throw up a few things and you tell me the answer. Okay, so we're gonna say probability liberal, probability male and liberal, probability someone's phone is vibrating, okay, so please write your answers here. And you just move these down. Okay, so I'll give you guys a few couple minutes to come up with your answers. If you are watching on YouTube, I'm going to pause the video right here so you can work out the answers yourself. Okay, let's go over this. Coincidentally, these numbers end up being the same, but we should probably check this out. Okay, so what is the probability that someone is liberal? We're going to have 46 out of 100, 0.46. Okay, what's the probability that someone is male and liberal? So this is going to be 0.21. This is 21 out of 100, male and liberal. We're picking someone at random. What's this probability that a person we select at random is a liberal man? 21 out of 100. Okay. Now, coincidentally, this one ends up being the same. This one is going to be 21 divided by 46. The 46 is the number of liberals. Okay, so this would be 21 out of 46, and over here we also have 21 out of 46, but this time the 46 is the number of males. Is the distinction here clear? Okay, I probably should have done something like probability of I guess I would write female given liberal, and probability of liberal given female. And over here I would have, what would I have over here? 25 over 46. And over here I would have 25 divided by 54. Okay. So study this. You'll probably see a quiz question similar next week to answering these types of things, and make sure you know the difference between female given liberal and liberal given female. Are there questions? Yes?
Yeah, when we do this, will it be a case where we're filling in the bubbles, or are we going to actually write out, like in the last example?
Yeah, no, you'll be filling in bubbles. Okay, so I'll have answer choices. They're all going to be in decimal form, though. Okay, and you'll have to pick the correct one here. Okay. Okay, let's take a short break. We'll come back after the quiz and continue. I mean, not after the quiz, after the break, and we'll continue on here.